Hello, welcome to Mechan 2040 Solar Mechanics. I am Globus from Sundial Academy. So this is the 9th tutorial of this course, which is talking about the applications of buckling of columns theory. So in our previous tutorial 8, we have already discussed about how to derive some important equations related to columns by using differential equations. Okay, so in this tutorial, we are not going to repeat those differential equations things. We will focus on how to apply those equations we derived to some real column problems. So in this tutorial, we will concentrate on the application of these equations. So at the beginning of this tutorial, we will give you some basic review. Then I will introduce you a couple of new concepts such as the effective length of columns as well as the slenderness ratio, and it follows that there are some example problems that worth you to have a try. So if you have no idea about how those equations come from, you might want to rewind to previous tutorial 8, which is talking about how the critical load of columns are obtained. Okay, so let's get started. So first, let's give you a little bit basic review on the critical stress of columns. Okay, so for different support conditions such as pinned column, fixed free column, fixed column, and fixed pinned column, they have different critical load which are located here. It's worth you to remember, or in case you are allowed to prepare a cheat sheet, you must jot it down, jot those equations down for different support conditions. Okay. Apart from the critical load concepts, in our previous tutorial, we introduced you the deflection curve of different support types, but actually for the deflection curve, it is not really our concern because, as what we mentioned in the previous tutorial, column buckling is not a kind of deflection problem. Instead, it is a kind of stability problem. Once buckling phenomenon occur, it could be very terrible, catastrophic. Okay, for the column buckling problem, the critical load equations are very important. You have to bear in mind with it. So next, let me introduce a little bit different view on how to read the critical load equations. Okay, so in the previous tutorial, we derived the critical load equations directly by using the differential equations, but here I'm going to introduce you a new concept called effective length. So effective length of different support type is saying that, okay, for each supporting type, what is the length of the bolt shape like this? So for the simply supported beam, pinned column, it is a bolt shape. Okay, so how long is the bolt shape of the deflection curve relative to the real length? Okay, so it is the concept of effective length. To repeat, we want to know what is the relative length of the bowl-shaped section to that of the entire length. So for the pin problem, the length of the bowl shape is given by L, approximately equals to L. Okay, and for the fixed free column, it is a little bit special. Above the fixed end, there is only one half section of the bowl shape. So if you extend it a little bit, you can see the bowl shape of this curve have a length twice to that of original shape. Okay, so the effective length of the fixed free column is given by 2L. Similarly, for the fixed column, you can see the bowl shape occurs in the midsection like this, and this length equals to 1/2 of the entire length of this column. Okay, and for the fourth case, so still remember we didn't use any analytical method to get the length. Instead, we use we use tangent KL minus KL vs KL, the plot, to find the x-intercept of this curve, right? So just now we did this. So actually, if we look at the bowl shape of this column, you can see that the length of this bowl shape is approximately 0.7 L to that of the entire length, right? So it is the concept of effective length. To make it clear, the effective length for pinned column is given by L, and for the fixed free column, it is given by 2L. For fixed column, it is given by 0.5 L, and for the fixed pinned column, it is given by 0.699, which is approximately equals to 0.7 L. So it is the concept of effective length. So the number K here is just an effective length factor that telling us what is the ratio between the effective length and the original length. Now we are going to introduce you a new equation, which is still defining the critical load of each column, but it could be much more easier. Instead of using the differential equations approach, we can use P critical equals to pi squared EI divided by the squared of the effective length. Well, you know the effective length is just the effective length factor times the original length KL. So the critical load is given by pi squared EI divided by KL squared. Okay. Also, we will introduce a little bit about the slenderness ratio, and the slenderness ratio is one of the important concepts in column engineering design. So there are some definitions that worth you to know. The first definition is radius of gyration. The definition is given by r squared equals to moment of inertia divided by the cross-sectional area, which means r equals to the square root of I divided by a. For the critical stress, we know for each material there is some critical stress, right? And exceeding that critical stress, there could be some damage on the material. So the critical stress sigma critical equals to the critical load divided by A, okay? But you know the area of the cross section A equals to I divided by r squared. Also, the critical load equals to pi squared EI divided by LE squared, as what we described in the previous slide. So we can simplify this expression a little bit by cancelling the moment of inertia in the denominator and the numerator. So eventually we will get pi squared E divided by the effective length divided by the radius of gyration squared. Now we are going to define a ratio which is called slenderness ratio. The ratio is just LE divided by R, so we call it the slenderness ratio equals to the effective length divided by the radius of gyration. And the fact is that the critical stress expressed in terms of slenderness ratio provides good estimate only for larger slenderness ratio. So in the following figure, you can see some experimental data, which is in red dots, as well as a corresponding plot. So from our experimental data, we can find that the critical stress of a column is estimated by the slenderness ratio, okay? So it is like this curve, okay? So this curve is very near to the experimental data or experimental outcome if the slenderness ratio is high. But if the slenderness ratio is intermediate or short, then the critical stress inside the column could be different. For the intermediate columns, the solid mechanics scholars will often use some empirical data, empirical equations, which is very complicated to explain at this level. While for short columns, the critical stress of a column is just very near to the yield stress of the material. If we want to use the Euler's continuous model to estimate the critical stress inside a column, then this model is only applicable to long columns. If we say we want to estimate the critical stress in a very short column or intermediate columns, then no, you cannot use Euler's continuous model of column buckling. Otherwise, it will bring you a very large error, say large error, okay? Or if you are talking about short columns, then it is hard to imagine error, okay? It will penetrate the ceiling, I guess. But anyway, so bear in mind that for Euler's continuous model, it can only predict the performance, the buckling critical stress of a column when the column is relatively long. Otherwise, it could bring you very large error, okay, especially when you're talking about short columns. Although the Euler's continuous model could give you a very large critical stress for the material, it is just that strong and it cannot withstand even higher stress. Okay, so as you can see, for short columns, the critical stress is very near to the yield stress. So now let's solve some examples related to the column buckling. So the first problem is talking about a column of 3 rods. So there are 3 rods like this, and each rod has a radius of r, and those 3 identical solid circular rods are placed together to form a compression member. So there is a load P applying on it. So assume we are dealing with pin end conditions. So this column, we model it as a pin end condition, and we are going to determine the critical load P critical in 2 cases. One is that we assume those rods act independently as individual columns. That is, we assume those 3 rods are now become independent columns, 3 simply supported columns. Okay, so first we deal with the first case, the critical load when the rods are acting independently. So for the simply supported case, we know that critical load for the simply supported case equals to pi squared E I divided by LE squared, where LE is just L. Also, for a circular cross-section, the moment of inertia is given by pi r to the power 4 divided by 4. So the critical load for each column, for each circular rod, is given by 1/4. The denominator is L squared. The numerator is pi to the power 3 E r to the power 4. Okay, then if we're talking about 3 columns, then we just times it by 3, then we are done. So those 3 columns can totally give you a critical load of 3/4 of pi cube E times r to the power 4 divided by L squared. Well, let's see another case that the rods are now bonded by a proxy and they function as a single member. The meaning is that now we are not dealing with independent columns. So assume now those 3 columns are now bonded to become some tough material. Okay, just like this. Okay, something like this. And for this very thick column, which is combined by all 3 circular rods, we make it simply supported like this. Okay, so what will be the case look like? So in this case, we have to recalculate the total moment of inertia inside this case. So the sum of moment of inertia for each column is calculated like this. So the first thing we are going to compute is about the individual moment of inertia. So for each circular rod, itself, it has a moment of inertia of pi r to the power 4 divided by 4. But if we calculate the moment of inertia about the y-axis for simplicity, then for the rest of those two columns, although those two columns themselves has a moment of inertia of pi r to the power 4 divided by 4, okay, there are two of them, but since they have some distance from the axis we concern, so the distance here is r. So by the parallel axis theorem, we have a plus distance squared. So the area for each of them is pi r squared, and the distance is given by r squared. So eventually, the moment of inertia of those three circular rods combined is given by 11 pi r to the power 4 divided by 4. And if they are functioning as a whole, then the critical load will be pi square EI L square equals to pi square E L square 11 pi r to the power 4 divided by 4, which is 11 divided by 4 times pi cube r to the power 4e divided by L squared. So as you can see, if we do some comparison, when they are functioning individually, we can see the critical load is about 3/4 of pi cube r to the power 4e divided by L squared. While for the second case, the critical load suddenly become 11 over 4 something, the pi cube r to the power 4e divided by L squared. So it is from 3/4 pi cube r 4e L squared to 11 divided by 4 pi cube r 4e L squared. So as you can see, the critical load has increased significantly. So the conclusion is that if you can really bond all those rods together and perform as a single piece of column, then it will bring you extra available critical load. So this is basically what is this problem talking about. So the moment of inertia effect takes very important role here. Next, we discuss about the columns in structure. It is a very easy problem actually. So here is a horizontal beam. This beam is supported at point A, and for this column is giving this beam an upward force. In another word, the beam AB is giving a downward force to the column CD, okay? So here is D and this is 2D. So we want to know what is the allowable load Q over there such that the beam will be safe. So to do this by simple statics, okay? So if here it is Q, then it is generating a moment of 3QD. Then consequently, there must be a force of 3Q supporting the beam AB, and consequently, the compressive load acting on this column will be 3Q. So for the column, which is here, you can see that for this column, it is simply supported. So critical load equals to pi square EI divided by the effective length squared. So for this section of the beam, it is simply supported, right? So the length is 0.6 L. So now it will now become pi square EI divided by 0.36 L squared. And you put everything you know L equals to 30 inches as we given, okay? And the moment of inertia of the square can be computed as 1/12 of 1.5 to the power 4 inch to the power 4. So eventually you will get the allowable critical load, which is given by 129 kilo-pound, and the safety factor suggests that the allowable load on this column will become 71.4 kilo-pounds. But you know the load acting on this column is given by 3Q. So now 3Q equals to 71.4 kilo-pound. So Q equals to 23.8 kilo-pound. So this is how we solve this problem. So in short, first we get the expression of the compressive load acting on column CD. Then we compute its critical load. Then we apply the safety factor 1.8 to get allowable load of 3Q. Then we get the allowable load of Q. So here is another question talking about your concepts. Consider it is a very long column of rigidity EI. One end is fixed and another end is restricted from rotation. So the column has a square cross-section of side length W. Then the moment of inertia will be 1/12 of W to the power 4. So here is a pin, and it is installed at an altitude of H. Let P be the allowable load of this column, and the L is the length of this column. Okay. Then if we take a factor of safety N, which of the following statements will be false? So the lower section is subject to the weight of upper section. So assume for the upper section there is some weight. A is that Euler's continuous model neglects the weight effect of column loading. B is that Euler's continuous model suggests that an optimized design is to locate the pin at an altitude of H is greater than 0.5 L. C, if we assume section A is a long column, then the slenderness ratio of section A should be less than this value 1.22 L divided by W for an optimized design. W is the side length of the square cross-section of the beam. If we assume section B is a long column, the critical load of section B is approximately given by this. Okay, so among those four choices, you are going to choose the false statement. And now you are suggested to pause this video for 5 or 6 minutes to think of it. Here is the solution. A is correct, C is correct, and D is correct. So here is the reason. A, Euler's continuous model neglects the weight effect of column loading. It is correct because when you are computing a column, you never consider the weight of it. So for example, if you cut the column in the middle, then you only have the external load or the support at the bottom. You don't have the weight of the column. C, if we assume section A here, the lower section is a long column, then the slenderness ratio should be less than this for an optimized design, where W is the side length of the square cross-section of the column. In our option B, here is the explanation, and one thing we have to bear in mind is that the critical load of A should be greater than that of B, because for section A, we are going to account for the weight effect of the section B. So for section B, there is some weight acting on the lower section A. So the critical load requirement of section A should be larger than that of section B. Also, if you look at this column carefully, you can find that for the end with a rotational constraint, it is just like a fixed end. And here is a pinned end. And of course, this is also a fixed end. And this is a pinned end. So both section A and B can be modeled as a column which is fixed at the end and pinned at the top. Okay, so both A and B, those two sections, can be modeled as columns which is fixed at the bottom and pinned on the top. This is why we have 2.046 pi square EI something over there. The length of the lower section is given by H, and the length of the higher section B is given by L minus H. So we can write the equation in this way. This is because the lower section A is subject to the weight of upper section B. And then, since this one must be greater than this one, which means H squared must less than L minus H squared. It means H must less than 0.5 L instead of larger than 0.5 L. So statement B is incorrect. Statement C, if we assume section A is the long column, then the slenderness ratio of section A should be less than this for an optimized design. This statement is correct. So first we start from the definition of the slenderness ratio. The slenderness ratio, RS, is given by LE divided by R, which is equal to LE divided by square root of I divided by A. But you know the moment of inertia of the square cross-section equals to 1/12 of W to the power 4, while the area of this square cross-section is given by W to the power 2. So moment of inertia divided by the area will become something like this. Also, the length of the lower section A is given by H, but the effective length is, as what we have learned, is 0.699 something, right? So we just say it is less than 0.7 of its entire length, which is 0.7 H. But you know that from option B, the explanation, we know that H must be less than 1/2 of L for an optimal design. That is because if H is too high, then section A will be too easy to buckle. Since H is less than 0.5 L, we can convert this to our next step. That is, we put our 1/12 square root to the numerator, and we take out W squared from the square root to be W. So it is 0.35 square root 12 L divided by W, and eventually you compute 0.35 square root 12 L to get something like this. So the slenderness ratio of section A must be less than this one, so that the design in this column will be optimized. Otherwise, if the length H is too high, then the design could not be optimized. Option D, if we assume B is a long column, then the critical load of B is approximately given by this. Well, it is directly correct based on the formula we already discussed. So among those four options, B is wrong. H must be less than 0.5 L so that an optimal design could be obtained. One thing I want to place stress on this MCQ is that in option CD, we assume section A or section B as a long column. This assumption is necessary because if you are dealing with short columns, then the critical stress, as what we mentioned in previous slides, the critical stress will change significantly, and consequently, the actual critical load could change as well. So for short columns, we cannot overestimate the critical load by using this Euler continuous model because you have the material yield stress as the ultimate limitation. Once the material is going to yield, you cannot further give it any load, okay? Otherwise, the material will buckle as well. So finally, comes to our last problem in this tutorial, which is a past homework problem. So here is a rectangular column with cross-sectional dimension B and H, which is here. It is pin supported on two ends, A and C. At the mid-height, the column is restrained in the plane of the figure, but is free to deflect perpendicular to the plane of the figure. Well, the meaning of column is restrained is that, from this figure, we know that this cross-section cannot deflect along the transverse direction of the section XX, but it can deflect in the literal direction. That is, for this column, it cannot deflect with respect to axis 2, 2. Instead, it can only buckle along axis 1, 1. So now we are going to compute the moment of inertia along axis 1, 1 and the 2, 2. So I1 equals to 1/12 of BH cubed, while I22 equals to 1/12 of B cubed H. So the question is that determine the ratio H divided by B such that the critical load is the same for buckling in two principal planes of this column. The meaning is that if we want this column to buckle along the axis 1, 1, then there is no constraint, then there will be a critical load. If we want the column to buckle with respect to axis 2, 2, then the effective length of buckling will be 1/2, because here it is constrained from buckling. That is, if we want to buckle it, then the shape will be something like this and this. The effective length of buckling will become L divided by 2. So we are going to find the ratio H divided by B such that the critical load, if the column is buckling with respect to axis 1, 1 and the 2, 2 are the same. So the thing is that we want to first find the critical load in terms of B and H, right? So first, we find the critical load of this column when buckling in the direction 1, 1. Then it is pi squared EI divided by L squared, and the moment of inertia is 1/12 of BH cubed, and we have pi squared E divided by L squared. If the column is buckling along axis 2, 2, then the length, effective length of buckling will become L divided by 2 for each section, C boy and boy A. Then this equation will become 4 times B cubed H divided by 12, which is the moment of inertia when buckling along axis 2, 2. Then pi squared E divided by L squared. So we are going to find the ratio H divided by B when the critical load of buckling are the same. So we connect those two equations together, we get something like this. Then immediately we can cancel this. Then we can cancel BH in each of the numerator here. Then eventually we will get H squared divided by 12 equals to 4 times B squared divided by 12, which means H squared divided by B squared equals to 4. Then H divided by B equals to 2. So those are all example problems covered in this tutorial. So here is the self-test and the grade estimate. You are encouraged to finish all those problems independently, but still, the grade estimate here is just for your reference. It does not reflect your true performance in the final exam or midterm exam or whatever. And thank you for watching, and see you in the last tutorial, which is the energy methods.